So last time recall that we covered the translation operator, and it's this little, I used different symbologies at the time, so I put like a delta in there, and then I later said, okay, let's make that delta an x. And let's see, what did I do with that? Let me remind myself what it is. Okay, I called it I minus some unknown operator. So I called it this, and then later showed this property. Where am I at? Okay, the commutator. I later showed the commutator of this thing is actually basically this, and I guess that's a little prime that I don't quite remember. And then later I showed that, let's see, what did I show? So this is also, I did that just with this, and then later I used this definition of the translation operator to show that you had, I'll write the whole thing out. Okay, so this is the part you want to pay attention to. Okay, so so this is like operator T, and then this is T operator, where T is the translation operator. Okay, the thing to pay attention here is I've got xk and kx. That's what you really want to pay attention to. Okay, and this from above, and then what you show is therefore that the commutator of x and k, and k is unknown, is I. I think that's actually a minus. I remember last time I had a little bit of a problem with a minus sign, and so I should look at the video. I may have screwed that up, but I don't want to. I'm sorry if I made a mistake. I remember at the time, last lecture, I was kind of fumbling. You may have noticed whether there's a minus sign there or not. And actually, I just realized I needed to look that up, and I didn't. The point of this was it was a rather complicated derivation, but I'm not getting you to try to like that's something you need to know. It's really about practice. I'm just trying to practice with resolutions of the identity. I'm just trying to practice with continuous variables in terms of direct notation. It really was entirely my purpose. So sorry. Yeah. So if this commutator with this unknown operator is I, and the commutator of I momentum is h bar, then you can figure out pretty quickly that the unknown operator is just p over h bar. So that's where we left off last time. And so, I don't want you to have to worry about oh, I have to be able to do that. No, you need to be able to manipulate direct notation. There's so, especially if you, and I'm praying you have looked at the current homework, you can do a lot of shenanigans with the direct notation. There's all kinds of little proofs and simple problems that can be set up. You saw a little bit of that with problem set 3. With X, it's a little bit, I even have a little bit more in my toolkit to come up with questions. So this was really just all about giving you some practice with that. By itself, it's not terribly important. Okay, now the next thing to note is that we often don't want to move in an infinitesimal amount. I think I went off on how much I resent the fact that partial of x is 1 over infinity but not 0. It drives me nuts. Anyway, I'll never get over that. Now the way to move something, a macroscopic amount, let's see, let's say micro, and hopefully you'll follow me in your notes, to macro. So I'm talking about moving not just some infinitely small distance. What you can do, and you remember that this is a property of the translation operator. You can just apply it over and over and over and over and over again, like n times where n goes to infinity. So we're going to do the limit as n goes to infinity. So a partial is 1 over infinity times infinity, so now it looks like it might be a little bit bigger than 1 over infinity, a little bit bigger than 0. So I'll just write that out again, and it goes to infinity. 1 minus I p h bar. Now what you can do is I'm going to replace the partial of x with a more macroscopic amount divided by n, some number over infinity, again, the n. Okay, now what you do is with this, you can start multiplying it out. This, again, maybe just stick to 2 of them and write those terms out. And then you can group all the powers of, well, there'd be a 1, and then you can group things by powers of p and h. And what you would find is that you could write this as a sum, some kind of sum. And if you look up what does that sum represent, that sum would be the Taylor series representation of this. And again, the book is obsessed with dashes. I don't know why. I'm just trying to reproduce it. So I hope you are looking in the book. The book is, sometimes the book is pretty good. It's half the time completely, when it's incomprehensible, it's completely incomprehensible. But anyway, so again, the way to prove this is to multiply it out, collect terms. You would see that it fits some kind of mold of a summation. That summation happens to be the Taylor series representation of this. That's how you go about proving it. Now there's one thing, and I kind of wish Abdul was here, because I know he's like me, that I know that mathematicians have to do things like perfectly, right? You can't just take a couple of terms and say, well, it looks like a sine, so we're going to say it's a sine. I'm sure the rest of the terms are a sine, right? You know what I mean? Like mathematicians, they want this to be perfect, not just to show like, well, it looks like it's heading in that direction. All right, so I found out how you prove that kind of stuff exactly, and that's on problem set 5. And let me just tell you, it's kind of fascinating. Okay, so what you would do is you actually take the derivative of this. And then if you want to say this is that, you take the derivative of that. And if they're the same, then it turns out there's a theorem of differential equations that say if their derivatives are the same, then the functions, then the originating functions are also the same. So I had to do that on a problem set. I just thought that was kind of neat, and I kind of figured, I actually was working on that before I knew who was all in here, but again, I knew that I'd get someone like me, like Abdul, because I know he's really obsessed with, like, it's got to be just right. And anyway, I was glad I did that, because that's how you actually prove those kinds of things. Anyway, so, okay, now, again, to follow the book, I'm going to just do a little aside here. I did want to follow the book. This will come up later, and so I find it strange that the book brings us up here, but I just in case you're following it, let me just mention this. Not to, don't worry about it if you're not reading the book, although again, I do think it's not a bad idea to familiarize yourself with the book. And whatnot, so I do want to reproduce some of that. Okay. They go off on commutator relationships. So there's some identities of commutators, and also, I don't think on problem set 4 or problem set 5, you have a little bit of a dose of that too. There's a problem where you have to apply some commutator identities. Now, another thing is again, I am going to try to avoid this, but in the world that this guy is from, this J.J. Sakurai guy who wrote the book, x of I and x of j, what he's really referring to is x, y, z. So like I of 1 is x, I of 2 is actually a y, and I of 3 is actually a z. It represents it this way. So when you see this would actually mean dimensions. I find that, again, very strange because x is x, right? Anyway, just look out for that. So that commutator is 0. And more importantly, this commutator is I h bar direct delta function I j. Okay, so I've been saying that the commutator of x and p is I h bar. But what I really mean by that is, x again, x in my world, x is x. And so therefore, I'm not going to bring up momentum unless I'm talking about minus IH bar derivative of x, because that just doesn't make sense. If I'm talking about x is x, and this is the derivative of y, what the hell? Why would I be doing that? But they feel the need to bring it up, that is in fact the case. If that's x and that's the ddx, then the commutator is IH bar. If this is the momentum in y, then it's 0. So that's what that does. So I don't know why they're bringing this up. I mean, this seems kind of stupid to me, but at the same time I actually know, because your book at this point talks about something called a Poisson bracket. And a Poisson bracket is, maybe don't worry about this right now, but let's say, let's say A an operator and B operator. This is a classical mechanics thing. I'm sorry, not operators, these are functions. It looks like this. So it turns out that when you're doing mechanics, like describing a ball rolling down a hill, or maybe a ball rolling through a something more complex, like a miniature golf course, it turns out you run into this. And again, I'm doing Newton's equations. It turns out that when you are doing like x and p classically, that the result is the same thing in quantum mechanics times IH bar, where of course A is now an operator and B is an operator. So the book mentions this, and I'm going to bring this up later. So I don't even care if you write it down, to be honest. But again, in classical mechanics, when you're doing like hard problems, like if I throw a ball, it moves in, it's going 50 miles an hour, and 1 hour it goes 50 miles. All right, I can do that in my head. But if I'm describing a ball going through a miniature golf course with some complex potential surface with some kind of functional form, you can probably figure out, the velocity and position of the ball over time. But you can imagine you're going to be doing some pretty deep mathematical, it's going to be complicated, but it's doable. Poisson brackets are one of the mathematical tools that physicists use to describe, okay, here's an example, like a satellite that has to be launched from here and land on Mars at the right spot. Again, Newton's equations are not hard, but that sounds hard, right? You would be using Poisson brackets as your mathematical toolkit to solve that kind of really complex problem. And here's what it is. And I'll explain, I'll even give you a problem in next week. I'm going to solve the motion of the spring, just for practice. No, we don't need to do this. But the thing is that it's crazy that commutators, if this is position and momentum in velocity and time world, classical world, and this is position and momentum in quantum world, this Poisson bracket and this commutator are the same. There's an IH bar, but whatever. So the book makes a really big deal. Physicists make a huge deal out of this. And I'll bring it up again to explain why, but I don't really think that it's something we need to worry about that much. I think so people keep saying it's kind of fascinating that this tends to happen. To connect the classical to the quantum, I just don't care that much. I mean, it's not like we avoid solving any, we're still going to be doing these hard quantum mechanical calculations regardless of Poisson brackets working the way they do or not. Anyway, so I don't take much stock in that, so I don't know why I'm bringing it up. Okay, just some other things, because I do have a homework problem on this, of course, commutator. So the book is bringing this up because later they're going to connect it to some Poisson brackets. Obviously, the commutator of an operator with itself. The commutator of an operator with a constant, like pi. And of course, I brought this one up before. If you switch this around, then you're going to pick up a minus sign for obvious reasons. Because AB is equal to minus minus BA, essentially. This isn't one, there's one that is in your book, that's in one of your problem sets. It's not this one. I just want you to be aware that these relationships exist, and sometimes proofs will pull them out. This one is in your upcoming problem set, but I want you to know that I have, all these have little hats, right? Sorry, these little headers doesn't feel special. I actually wrote out the identity, so it's not like you're going to be doing it and you're going to be like, oh, it's not working and I don't know why, and then you don't realize you need to use what I just wrote like right now. No, I spelled it out because I don't need this to be like a memorization game. Actually, sorry, it's this one. This is the one that is in your, it turns out you can have commutators and commutators, which is a bit of a biznknocker, but so on your upcoming problem set, you actually have a commutator and a commutator and a commutator and a commutator and a commutator. It's like it's nested, and but then I showed you that one is complicated enough that it's one of those ones I broke up into parts. And you've seen me do this a zillion times now. I recognize that it was just ridiculously complicated, so I broke it down into parts so that you just do each part, and then you'll figure it out. Anyway, this is in your book. I just again thought, just to show it to you, I just kind of followed the book, although I don't always follow the book because it's kind of funky. Okay, and the main point, I only want to do one thing today. I'll use up our time, but what I wanted to do was just more proofs, and again, more practice with quantum proofs. And what I'm going to do, so forget all this. Again, this is part of your next homework, but there it is, and it's also in your problem set. So maybe what's kind of good to know is that you can do things like take commutators and commutators. I guess it's good to know you can do that. And there is one other. This comes up. Oh, wait. This might be in your current problem set. Sorry about that. I think this is something that is explicit or actually just turns out to be part of the solution, although you actually don't need to know it. There's this circular relationship. This is kind of like the Euler relationship, dx dy at constant z, dy dz at constant x, dz dx at constant y is equal to -1. Remember that? That's a big one in thermal. So this is kind of like that. This is like the Euler relation. Anyway, and actually I think that you're actually going to run into this on your current problem set, but it's not, you don't need to know that to do it.
Do they all wear hats?
What's that?
Do they all wear hats?
Say
Hats.
did I not put hats? Yeah, everyone gets a hat. I got to get back on that textbook. I mostly finished the thermal one, and I got funding to do the quantum one. And I'm always really careful with this because I know when you're learning this for the first time and you see something, for me, I'm just used to this, and jaded and whatnot. But when you're seeing it for the first time, I know if you see something wrong, if you're like me and Abdul, it's going to drive you nuts. So anyway, it's not necessarily a bad trait for new grad students, but okay. Anyway, all right. So today again. This is a little stupid, but it's just a matter of practice getting used to this stuff. What I'm going to do is I'm going to prove this. I don't know why I need to. Okay, let's say p squared over 2m. I don't know why the book needs to do this, but I thought I would do it just because, for continuity's sakes, and to practice with our Dirac notation. Okay, so we know that this is the case, and remember, we actually can prove that from Maxwell's equations, right? Remember, lecture 1, we talked about this. Okay, so regardless, what you can do with this is simply take, so momentum, you just get rid of the 2m, so you got the derivative of h bar squared And I think you can take a derivative of a double derivative. I think that's perfectly legit. And you can show that the momentum operator is this. You know, kind of take it for granted. But the book wants to do this formal proof. And again, I'm like, what? But then I thought, let's do it. Let's do it. Why not? So anyway, so I'm pretty sure, so what we're doing is we're proving the momentum operator. There actually is one or two useful points. It's a little bit more than an exercise. There's actually one thing that's kind of fascinating about it. So I thought we'd do it. That'll be all we need to do today. Okay, so what do I want to do? All right, so I'm going to start with the translation operator because that has momentum in it. And we'll apply that to some unknown state. And of course, this is the momentum operator. And I better keep, okay, so this is kind of painful. I told you the book is nutty with these little dashes, but I was very careful with my notes because these are bookkeeping marks. If I'm going to resolve an identity, then I need to make sure that that an x, if I'm going to resolve an identity and have a partial of the x dash, I need to make sure that it's not confused with this part, which is how much it's being pushed over. Right? So it's just a bookkeeping thing. Just your book. I get lost in all the x dashes sometimes. That's why I've been trying out my own notation about that. Anyway, okay, in this case, I have to be careful. Okay, so translation operator is this. You notice I wrote it kind of backward. You'll see why in a minute, but it doesn't matter. Now what I'm going to do is resolve an identity. And the partial, when you see in the book, or I'm not doing this too, the partial is a number. It can go anywhere. It can go front or in back. And so I'll manipulate where the partial is sometimes. If it's in between an outer product, you can go outside of it. Okay, here's the outer product. Okay, so so I slipped in the resolution of the identity between. Remember, you can kind of slip these around, kind of wherever you need to. Let's see here. All right, so then this. Let me put this over here. This is alpha. Not much to it. Okay, now also, let me point out how this is going to go. Where I'm going to prove that momentum is this, right there. So I'm going to solve for P. And P's right there. Okay. All right, now this thing, not much to this. I'm going to apply it to this ket. And so the ket is displaced by that. And then I have the position representation of state alpha. Okay, now this is kind of cool. This is some of the things that, remember how I said you want to think of extra state ket not so much as the x-axis, but as a point on the x-axis. I'm just writing this part over again. The reason I brought that up and really harped on it was actually because of this lecture. I'm about 1 week ahead in terms of my notes and lectures, which is not that good, by the way, but that's my problem. Okay, this is the cool thing. You see, I just took I just said that what's left and right is kind of irrelevant. Did I move to the right? Am I at the left and moving to the right, or am I at the right and moving to the left? What does it matter? Right? So remember what this is that I'm at a position, I'm at this, remember, I said think of these as positions, not the entire graph. This is 5 nanometers, so what I want to do is look at the wave function at 5.1 nanometers. However, I could have been at 5.0 nanometers, and that's 5.1. See, it's arbitrary where these positions are. So I could either say I'm moving forward, or I could say that my my landing point is 5 plus 0.1, or it's 5.1. And I'm simply starting at 5.0. Or I'm starting at 5.0 and I'm moving to 5 plus 1.1. Yeah, right? See what I mean?
Is there like an identity that like?
No, it's just logical. So again, if I'm moving to 5.1, I can either define x as 5 and that's 0.1, or I could just say x is 5.1. So these aren't really the same x. So if I'm moving to 5.1, then x is 5. But if instead x is 5.1, then this is 5.0. Anyway, it's a little silly. It's actually kind of silly. It's a little unsatisfying because we don't like math to be silly, but that's kind of a silly thing. Okay, now I'm going to spend a bit of time on this. I'm going to write this over again. Actually, what am I going to do? I am actually going to resolve an identity here on alpha, and you'll see why in a minute. And I better use dx, x, alpha, no, xx, alpha. And I see that I needed to give myself a little bit more room. Okay. Now, again, I hope that this isn't like, it's not that bad, right? This is nuts. Watch this. Watch this. We'll spend some time on this. Okay, dx. Okay, there's the ket, right? Remember that this is the actual, like this integral this is like the x-axis, right? So that's why this is like the whole wave function. Not just that. That's just a part of the wave function. Anyway, I can't hammer on that enough. Okay, so there's the ket. Now I'm going to bracket this off. I'm now going to have x alpha minus this partial. There you go. Ta-da! Now the thing is, the book just writes this down, so clearly, this is that. All this stuff in the bracket. Maybe I'll put a little bracket there, right? Okay. So there's the bracket, so there's the bracket. So anyway, you see what that turned into. And now that bothers me. Now I have to do that. I can't have both. Right? Those are the same thing, right? Right. Tell you what.
Why not?
Tell you what. We're going to look at it again. And this is why sometimes when, I get not to pat myself on the back too much, but this is why sometimes we need an instructor to walk you through what the hell just happened. And the book, this is again where the book really kind of chokes. It probably should explain what the hell this is. It's unbelievably, you're going to laugh when you see how easy it is to follow this. Let me just finish this up. Because I don't want to get too far off track. And it's going to take like 5 minutes. And, I'm not sure how much time we'll have after that. So anyway. So that was actually one of the reasons I wanted to stop, so that when you understand why you're going from that thing to there, again, it's going to really help you get what this is. And that's one of the main reasons. Once I figured that out, I was like, oh yeah, I really should show people that, so that you understand what the heck is going on. Okay. So now I'm just writing again. This is nothing. It's just a resolution of the identity. This is going to cancel out, by the way, in a second. Oh, I'm not lined up, am I? Oh, that bothers me. I need to be further to the left. Okay, now I gotta, okay, so notice how the integral is actually going to distribute into so I have two terms. Remember when you're integrating a function, f plus g, you're actually doing two integrals, right? You're integrating f plus the integral of g. So that's what I'm doing here. So you may notice that, look what I've done. cancel. Now you notice that I'm getting closer to isolating just the momentum operator. Okay, then the leftovers of this what the hell is it part, which again, you're just going to laugh and be like, oh wait, that's what that is? That's easy. And you can see that I have painted myself almost to the very edge, which is what I strenuously try to avoid. Okay. So again, the integral of f plus g is just two separate integrals of, I guess there's, f minus g is integral of f minus the integral of g. Okay, so these have canceled. And let's see, what have I got? Oh, this is actually it. Okay, so I, momentum operating on a ket for h bar. I'll move the IH bar over in a minute. Which equals the integral dx. And hopefully I'll write it out a little bit nicer. Okay. Okay, so this is funky. What's up? What's up?
One negative sign.
Minus, yes. Yeah, what if I have to, yeah, there's definitely a minus sign. To figure, oh, my notes have the minus sign disappearing. I'll have to figure out where that's, oh, I've messed something up here. Yeah, I seem to be missing a minus sign in my notes. Well, I'm just going to work on the derivation further and figure out where the heck it's gone. Yeah, damn it. I'm sure that it'll go away or it actually makes sense once I go further, but here's part of the deal. Okay, now this is one of the things also I wanted to bring up. This is actually the momentum operator. So here, and again, so that I don't confuse myself. Now these are constants. They can come over, right? What have I done? So 1 over I is minus.
So another thing is...
Oh, no, wait. That H bar is on top. Oh, one second. Right? I just brought the constants over.
Oh no, I had the previous step. We cancelled out dx double dash in both the sides.
No, wait a minute. No, I wrote down the translation operator incorrectly. That's what I did. The translation operator. I'm sorry. Look what I did.
Oh, yes, yeah.
Sorry, it was going so. This is, and then I'll fix my notes, and then the next time I teach you, that won't happen. That's not when you're in the first class. You gotta remember I was telling you this, right? When it's the first class, there's screw ups, and you actually should have seen the first time I did PChem. I mean, people still are happy with me overall. I'm glad about that, but trust me, I made mistakes. Okay, so now the minus sign is gone. Okay, yeah, I can't believe I did that. Yeah, so if it was, if that was like an adjoint working on a bra, then the adjoint in that case is plus I, not minus I, but that's not what's happening. Okay, well, cool, it's worked out, and that's because this is minus I H bar dx. There we go. And that partial doesn't look good. It has to look good. There we go. Okay. All right. Now this is where this is really funky. It turns out that this is actually the definition of the operator in Dirac notation. So I'm basically done, right? And this is funky. The reason that this is so funky is that I can see a resolution of the identity here. I can see that, right? Integral dx outer product xx. But the operator has slipped itself in between, and that means you can't just take it out. Can't do that, right? It's tempting, but in a resolution of the identity, that bra and ket, they have to be right next to each other. That's not something you're allowed to do. So that's why we're actually done. But at the same time, then, where the heck is my? Where was I originally? At the very top, momentum is minus IH bar ddx. Where is that? Okay, the way around that is, to show that part, you have to do this. So I'm done. I'm done. So that's just a really funky thing. And the book even uses that identity later on. You have to do this. And again, I have to be careful with my bookkeeping, so I have to have a little dash there, otherwise it will get confusing with some of the others. Okay, all right, so remember the partial is just a number that can slide out of the way. All right, now I've got a Dirac delta function, which is means that my integral is going to go away, and all my x's turn to x dash or the other way. I never keep it straight. Doesn't matter, that's why I don't really keep it straight. Okay, so remember this is a Dirac delta function. And I really love Dirac delta functions because they make integrals. I hate integrals, but they go away when I have a Dirac delta function. And so then this ends up being h bar, and how do I do this? Okay, so wherever I see an x, I have to do an x dash. Not that it matters at all, but so there you go. Oh, I already peed. Okay. Now, where's the minus?
Yeah, the minus here.
Yeah. See that on screen. Anyway, so there you go. Now it looks like what we expected to. But you see that we actually have to be a little careful with how we use momentum and Dirac notation. So, but there it looks like, and then like I say, mostly you got some practice with this, and that's really my main goal is to do that. Okay, now remember, I said I was going to explain where is it? I think it's on the previous board. I was going to explain that this part. I'll explain that. Because I was staring at this for the longest time too. And I was like, why the heck didn't the book explain this? What the heck? Where did that come from? And I just stared at it and I realized, oh man, that is unbelievably easy. And you're going to laugh. Okay, so remember, all right, so the way to do this is to look at a graph. Here's a wave function, and here's x. Okay. Now, when I look at this, let's see. When I look at this, I'm somewhere in, I have knowledge of a point, and what you're doing is you're querying you're querying what the wave function is at some other point. So for those at home watching, I hope you can see this. I shouldn't be drawing so small. So I'm here, and what this is a query of what's over to the left. Right. So I have knowledge of this point, but I'm doing this kind of stuff with translation operators, so I know I did a little funkiness when I did this, but all this is saying, hey, what's to the left? This would be the wave function to the right, and this is the wave function to the left. So that's what that means. Okay, now let's look at this. What does this say? This says, take this point. I'm going to start with the same point. Go a little bit to the right of it. And we're going to take that spot, and we're going to subtract the derivative times some, this is rise over run times run, right? This is the slope of the line. So here, let me zoom in. Here's the slope. Here's a line that has a slope. And what you're doing is you're traveling along it to some other point. You follow me here? So if you're at a point and you want to move to the left, you would want to know the slope and then how far. What's the slope? It's like a response times how far do you want to go. And that minus sign means we're moving left as opposed to right, which I kind of wish it was positive. We tend to like to think of moving right more than left, but anyway. See what I mean? Actually, it's really easy. Right? Just, if you're going to move to the right, this is how much the wave function responds when you move to the right, left. When you move to the left, how much does the wave function respond? So, yeah. See, so like in this case, it's my little close-up, the wave function is like 0.99, and it looks like it actually goes up a little bit. It looks like it goes to if I move to the left, the wave function actually rose a little bit, so the wave function is more like, instead of being 0.9, it's 1.00. And so that slope, that's a negative slope. So minus 1 times some minor step, it has caused a slight increase. Anyway, I'm being like way too specific, but yeah.
So it moved by a factor of that d wave function over dx times dx the whole time.
Well, yeah. I mean, so I actually, you're kind of muffled. I mean, again, this is like when you were learning about functions and slopes. You're actually seeing that again. It's under a different context, and that's why you may have some trouble, seeing it. That again, I'm here and I'm querying here. So the simple way to do that is to know what the slope is, and then right? Middle school, right? And the slope is the derivative, and dx is infinitely small. That's why this works out so well. And the change in y, that's the change in the wave function, which is what that is. What is the wave function if I move to the left? It's this. Or, yeah. Now I'm a little confused with deltas, but anyway. Yeah. Not hard at all. So, okay.
Cool for the momentum operator proof, but are we gonna apply this specific concept to maybe some other stuff that we might have to prove?
There's a proof where later in the book where they mention where they use this definition of the momentum operator. So at one point you'll see this, and then you'll see this. I don't even know if I'm actually covering that. I don't think that I am. But in your book, like in a page or two, when they've done this, and again, this is really one of the more outlandish things to follow, especially because of that thing I just talked about. There's another proof when they use this, and this looks really funky, right? And it really is the same momentum operator that we've known. It's just it's harder to see that under the layers of direct notation. So that was another reason I wanted to do this, was to show you momentum is still the derivative of x. But in the context of direct notation, it ends up being a little bit like, what? It's a little hard to follow. It looks a little harder if we were not using direct notation. Traditional chemistry, you just see this. Direct shellac synthesis and Ketz intervals. In terms of are you going to use it for anything? No. Again, the book applies this here. If you're following the book, that's where it comes from. We're not going to use it again. Again, I just want to practice. And like I say, I really hope that this kind of useful, this bit was kind of useful so that you really see how these kets, are just, this is 5 nanometers, this is 5.1 nanometers, 5 nanometers, 5.1, space is relative. Yeah?
Yeah, that makes sense. I just didn't know if I was going to be able to, like, apply that to something. Or like.
I don't know, I could either.
Recognize that that's what I should do to, like, go to the next step.
Well, like I personally, I don't think I'm not walking around with this in my head. I can tell you that much. I mean, I do this enough that I do know that momentum is minus IH bar dDx. Now that is something I will probably remember when I'm 90, and then I won't remember because either I'm dead or I've forgotten everything. That I'll remember. This, no, I'm not going to remember that. So, if any kind of proof, if you need to, if I don't know what I'll have on the next exam because I just haven't thought that far ahead, unfortunately. But if you needed to use this, of course I'd give it to you.
I have one more kind of dumb question. In the very first step, when we started with the translation operator, yeah, does the dx double prime cancel in the next for the next line?
Oh yes. Oh my God. I'm sorry. I forgot to mention that. Yes. Right. Right.
Yeah,
Right.
Because
it's a number.
Right of the equal sign.
Yeah. Sorry about that. Yeah. I should have pointed that out. This canceled out at this step. It was because I wasn't able to do that previously because this thing was here. This thing was here, and then that was canceled out by that business I was just talking about. And then that partial is just a number, a small number, but on both sides, and then I just can eliminate it. Yeah, when I was prepping for class, I actually remembered to say, hey, point out to your, say to myself, point out when that goes away. And I forgot.
So I had another question.
Okay, but we actually, I have to go.
Yeah, sure.
So,
Maybe next time.
real quick. You have to go, I have to go. Real quick.
Okay, it says that dx on the left hand side was not inside the integration, but in the right hand side it was inside the integration. So we are taking it out as a constant, is it? dx double prime.
No, remember, this isn't a derivative, it's a number.
Oh.
A partial is a number. It's a number that's basically zero.
Yeah.
And it has units of nanometers. Partials are numbers, they're numbers that are very close to zero, and they have units. That's all you need to know. I'm treating this like a number, but I can because it is. Partials are meaningless though, because they are zero. Partials do nothing. Partials either have to be integrated, and that's where we get the calculus of integrals, or you divide one partial by another partial, and then you got, then it's a derivative, right?
Yeah.
But really you want to think of it like a slope. It's like 0 over 0, but in your mathematics, at some point you should have learned limits, and you know that 0 over 0 is indeterminate.
Yeah.
It's somewhere between 0 and infinity. So when I say df dx, it's 0 over 0, but the way that those zeros balance each other out is such that it's the slope of the function x, function f. Yeah, that's how they balance out.